So let's think about this a little more, about how solutions are formed. So here we have an example of sodium chloride, table salt. And what sort of forces are holding the sodium and the chloride together? Ionic bonds, right? These are ions. So we have solute-solute attraction that's holding the sodium chloride together. And then our solvent that we're looking at is water. And between water, the water molecules, we have attractions as well, right? This is a solvent molecule, that's a solvent molecule, so they're calling this a solvent-solvent attraction. We just learned that the strongest force between water molecules is called hydrogen bonding. So in order for the sodium chloride to dissolve in the water, there has to be interaction between the water molecules, the solvent molecules, and the solute molecules. And there has to be interactions between the solvent and this anion as well. If the interactions between the solvent and the solute are similar in strength to the solvent-solvent and the solute-solute interactions, then it will dissolve. Not all ionic compounds are soluble in water. Some examples are calcium carbonate. In calcium carbonate, the attractions between the calcium ions and the carbonate ions are too strong, and it won't dissolve. So I do have a goofy analogy for this one. Let's see, which one should I be? I'll be the water. Okay, so imagine, see, I'm of Swedish descent, and my husband is of Japanese descent. So we say that our children are half samurai and half Viking. But I can pick on those two ethnicities because we are those, and so you can't get accused of being racist or anything. So let's say we had a room full of Swedish people and Japanese people. Now the truth is that most Japanese and almost all Swedes also speak English, but we're going to pretend that they don't. Okay, so we've got Swedish people who speak Swedish, Japanese people who speak Japanese. Are they going to interact very well with each other? No. So if the water molecules are the Swedes, they're going to speak Swedish to each other. There will be interaction between them. And down here you've got the Japanese, and they're speaking Japanese to each other. And there's no common language that they have that they can interact with the other kind. And so they're going to tend to form clumps of Japanese people and Swedish people and Japanese people, right? They're not going to mix. And that makes sense to us because we understand how that works, right? Yet people who don't speak the same language, it's really hard to communicate. Well, we can think of these types of interactions as being a little bit like a language that these particles speak. If they speak the same language, they're going to mix. If they don't speak the same language, they're not going to mix. So the language that the water molecules speak is based on electrostatic attractions that are permanently there. The hydrogen bonds, and those are very, very strong. And the language that the sodium and the chloride speak is ionic bonding, which is also based on strong attractions between opposite charges. So these ionic bonding interactions are similar to the hydrogen bonding. And so this ion feels pretty comfortable interacting with a water molecule because they speak that same language. And that's where that expression like dissolves like comes from. Ionic compounds are like extremely polar molecules. So polar molecules speak the same language as other polar molecules, and so they will mix together. Something like oil is nonpolar. It doesn't speak this same language as water does. Now these guys, sodium and chloride mix really well with water. It is important, like I said, to remember not all ionic compounds dissolve in water. And that's because sometimes these guys are so stuck on each other that they're not going to interact with the water. So let's look at how salt dissolves in water. So here we've got our sodium chloride, and it's all real stable and happy because we've got these alternating positive and negative charges, and this is a crystalline solid, and it's all arranged, and it's ionic bonds, and it's really stable and strong and high melting point and all that good stuff. And so we throw that into a beaker of water. And what happens is these water molecules speak a language in common with these ions, because this water molecule has a negative end, and so the negative end is attracted to the chloride, which has a positive end. I can't see the charges, and I'm not thinking very clearly, apparently. The positive end, the hydrogen part, is attracted to the negative ion. And so we get these water molecules clustering around the chloride, saying, "Hi, how are you? Come on out and play with us. Come on." And they're speaking this same opposite charged language. And then over here, because water's kind of two-faced, right? It's got a positive end and a negative end. And so over here, it turns its back, it turns the other way, and shows its negative side to the positive ion and also makes it feel comfortable. And so this sodium ion is very happy to go off surrounded by these water molecules, because those are replacing the interactions that it had with the chloride ions. And so the water molecules surround it and replace those interactions and allow those ions to move separately and become soluble in the water. So this is just kind of rehashing. But here we take this ordered crystalline lattice, we put it in water, and because the water molecules are surrounding each of these ions, the ions separate and move, and they become uniformly distributed throughout. They disperse. So it becomes homogeneous, as opposed to just salt crystals sitting on the bottom of a beaker of water. Well, you can only dissolve so much salt in a beaker of water. And so we talk about solubility. Solubility is defined as the amount of the compound, we usually express that in grams, that dissolves in a certain amount of liquid. So as an example, the solubility of sodium chloride at room temperature is 36 grams of sodium chloride per 100 grams of water. So if you have 100 grams of water, you could put 36 grams of sodium chloride in it, and it would all dissolve. If you put a little bit more, it would not dissolve, because that's the limit. It can only hold so much. So a solution that is at that solubility limit, we say, is saturated. Saturated is full, right? You think about a sponge that's saturated with water. Is it going to soak up any more water? No, it's full. A saturated solution is holding the maximum amount of solute under those solution conditions. And the solubility does depend on the temperature. If we take a saturated solution and add more solute, it's not going to dissolve. And you can try that at home with salt and water or sugar and water if you want to. Dissolve, put some salt in the water, stir it till it dissolves, and just keep doing that. Eventually you'll get to a point where it was all dissolved, but then you added a little more, and it won't dissolve no matter how much you stir it, because the water is full. It can't surround any more salt ions. So we have a saturated solution, and we can also have an unsaturated solution. We could put more solute in. It's holding less than the maximum amount. If we added a little more, it would still dissolve because it hasn't reached that limit. And then we have the really crazy one, the supersaturated solution. Supersaturated solution holds more than the normal maximum amount of solute. That seems impossible, doesn't it? How can you have more than the maximum? Well, a supersaturated solution is unstable. These are formed under special circumstances. When you open a can of soda, you briefly have a supersaturated solution. Another way that can happen is if you if you create a saturated solution at an elevated temperature, you heat it up, and then you let it cool down without disturbing it, some compounds will form a supersaturated solution. Sodium acetate is one of them. And then when you disturb it by even putting just a tiny crystal in that test tube of supersaturated solution, the solute will precipitate out of the supersaturated solution. Here's an illustration. I'll try to actually do this demonstration for you in class, in lab, because it's just really cool. This is a supersaturated solution of sodium acetate. And when it's disturbed, even just by touching it with a glass stirring rod, you see all these kind of like fingery things here? That's solid sodium acetate precipitating out of solution. Sodium acetate, a saturated solution, contains so much, well, back up. Back up. Okay. When it's done here, this is almost entirely solid sodium acetate. You can actually tip it upside down and nothing comes out. It's really, really cool. We talked about solubility rules before, and we use those to predict which ionic compounds dissolve in water and which ones don't. Those give us a qualitative description of the solubility of ionic compounds. They say, well, this one does and this one doesn't. Some ionic compounds like calcium carbonate are insoluble because the attraction between the ions is greater than the attraction between the solvent solute. Between the solvent and the solute. That sentence just kind of went over a cliff. And at this level of understanding of chemistry, I cannot explain satisfactorily to you why some of these ionic compounds dissolve and some don't. So we just have to kind of leave it. Molecular solids, some of these dissolve depending on whether the solid is polar. We know that table sugar dissolves in water, right? Table sugar is polar. If we look at the structure of sugar, it's got a whole bunch of OHs hanging off various sides of it. It's very polar. It's soluble in water. Nonpolar solids, like lard and vegetable shortening, are not soluble in water. They're generally insoluble. Did I miss one? No, that's it. Okay. So electrolytes versus non-electrolytes. Electrolyte is a word that gets used a lot. What does that make you think of? Gatorade, right? Yeah, you've been exercising, you need to replace your electrolytes. Well, that may be true. Electrolytes are dissolved ions. And when you sweat, you lose some of the ions that are dissolved in your sweat. So you've got sodium and chloride and potassium, a little bit of magnesium. And if you lose too many of those, it's not good for your body. And so, yeah, you do need to take in salt. Now, the bad thing about Gatorade is that it contains a lot of sugar. And you really don't need all the sugar. And sometimes you get to a point where you actually do need the electrolytes, but most people don't. They just like the taste of it. And they feel, well, I was sweating, so I need Gatorade. Yeah. Water actually works better most of the time. But when we use the word electrolyte, we are meaning the same thing as when the Gatorade people talk about electrolytes. Electrolytes are dissolved ions. And so when we talk about a solution that is an electrolyte solution, it has dissolved ions in it. Non-electrolyte solutions contain dissolved molecules. Molecules are neutral particles. So if we have sugar in water, sugar doesn't form ions in water. So this is a non-electrolyte solution. It'll probably show up later because I'm jumping the gun on everything. Electrolyte solutions will conduct electricity, and non-electrolyte solutions do not conduct electricity. And if you see over here, we've got this light bulb. We're going to mess around with that on Thursday in lab, and we're going to see exactly how that works. The solubility of solids varies with the temperature, and it's not consistent. Some things, the solubility varies a lot with temperature, and some things it varies not very much at all. Here we have sodium chloride. We have temperature on the x-axis and solubility in grams of solute per 100 grams of water on the y-axis. And we see that the solubility of sodium chloride does not change very much between freezing water and boiling water. The whole range of water in the liquid state goes from what, maybe 33 up to about 40, not much change. Then we look at something like potassium nitrate. Potassium nitrate has a very low solubility at 0 degrees Celsius, and it's through the roof at about 55 degrees. So here you can get an equal amount of potassium nitrate and to dissolve in water. So it's half and half. And if you go higher in temperature, guess what? This line just keeps going. Very, very soluble in water. But generally, the solubility increases. See, all of these guys, solubility is increasing with temperature. There are some things where the solubility decreases, but those are unusual. This variation in solubility with temperature allows us to purify solids, a technique called recrystallization. So what you do is you take this solid that you're wanting to purify and you dissolve it in water or an appropriate solvent at an elevated temperature. So you may make a saturated solution of this substance in, almost boiling water, really hot. As the solution cools, you let it cool slowly, the solubility decreases and some of that solid crystallizes out. It precipitates out. If you let it do that slowly, the solid will form beautiful crystals as it cools down, and that crystal structure is going to tend to reject impurities. So maybe there's some other ions in there that don't belong in that solid. Maybe you're crystallizing sodium chloride and there's some potassium. The potassium's not going to fit in the crystal. And if this precipitation happens slowly enough, it will get excluded. And so you can get much more pure solids using this technique of recrystallization. Rock candy is made by recrystallization of sugar. And that's something you can try at home too. I tried this once when I was a kid, but I didn't really know what I was doing, and so never got anything to happen. You need to make a saturated table sugar solution at an elevated temperature. It takes a lot of sugar. So you've got hot water, very hot water, and you just add sugar, and you add sugar, and you add sugar until no more will dissolve. And then you put a string in that solution, let it cool, and just let it stand. And yeah, you got to wait days. Okay, it's not just 5 minutes. You wait days. But as the solution cools, it becomes supersaturated, and the sugar will crystallize out of it. And you'll get these big, beautiful crystals growing on this string. And that's actually how they make rock candy. It's just pure sugar.